So, good morning, everyone, and welcome to this lecture. This is fourth lecture number 2, and in this particular lecture, we will be winding up your magnetic force. If you remember, in the last class, we had discussed what will happen when you have electric and magnetic field both coming into the picture. Well, we'll have to find out the electrostatic force from the formula Q into E, and then you need to find out the magnetic force using the formula QV cross B and then add them vectorally to get the results. Now, questions which have both electrostatic and magnetic field can be very difficult, but those questions are not going to come. What type of questions are going to come? We will discuss them case by case, and once we discuss them case by case, one of those case would be coming in your exam, and depending on which case is there, you should be able to solve and understand all those cases. Now, the first case that we are going to do in this one will be the case when all these three quantities are parallel to each other. What three quantities are parallel to each other? What three quantities are parallel to each other? Case number 1. Case number 1. Both E, V and B are collinear. I mean, they are parallel to each other. V, velocity, is parallel to electric field, is parallel to the magnetic field. So the case may be like this. As you can see here, the electric field is going in this direction, the magnetic field is going in this direction, and the velocity is in this direction. It could have been a different case as well, where electric field might be going anti-parallel, magnetic field might be going parallel, and so on. Now, in this particular case, what type of motion the particle will have? All the cases, all the three things are parallel. What type of motion the particle will have?
Accelerated motion.
What type of motion will the particle have? Circular. I mean, how will be the trajectory?
Linear.
Yes,
Linear.
it will be in a straight line, because magnetic field is parallel to the to the velocity. The particle will move in a straight line, and because of this electrostatic field, the speed of the particle will keep on changing. The electrostatic field will keep on changing its speed, and the particle will be moving in a straight line in the original direction. If your initial velocity is 0, then also the motion would also be same. The particle will move according to its acceleration. Do we understand this? Particle will move in which direction? In the direction of electric field. If the particle is positively charged. If the particle is negatively charged, it will move opposite to the direction of electric field. Do we understand this?
Yes.
I'll give you 2 minutes to note this down. Then we move on to the next case. And the next case is like this. Case number 2, if I make electric field is parallel to magnetic field, and let us say it is perpendicular to the velocity. So if I draw this diagram, the diagram may be like this. Your velocity may be like this. Your magnetic field may be like this. And your electric field may be like this. What type of motion will this particle have?
Uniform circular motion.
Because of this electric field, the x component of velocity will keep on increasing. Because of this magnetic field and this velocity v, the particle will move in a circle. So the motion of this particle will be helical with increasing pitch. Which will be increasing because its x component of velocity will keep on increasing. So the pitch of this helix will keep on increase, and because of the perpendicular component of velocity, it will be moving in circles. So the trajectory would be helical with increasing speed. I'll give you 1 minute to note this down. Then comes the next case where electric and magnetic field are parallel to each other, but the velocity is not parallel. Velocity is not at 90 degrees. Velocity is at an angle like this. What type of motion will this particle have? As you can see, this velocity has been broken up into two, one horizontal component and vertical component, to make you understand what is going to happen with this particle. Can you tell me what type of motion this particle is going to have? What type of motion this particle is going to have? Any idea? It will have a motion like this. Again, this is the same path, helix with increasing pitch. The pitch of this helix will keep on increasing because of this electric field. The velocity will keep on increasing because of this magnetic field and this component of velocity. It will be moving in a circular path. It will be moving in a circular path, but it will be also going ahead. The x component of velocity will keep on increasing, and therefore the pitch will keep on increasing. So this is also a case wherever E and B are parallel and velocity is not parallel, then that is the case of helix with increasing pitch. I'll give you 2 minutes to note this down. Then there is the third case where all the three vectors are perpendicular to each other. Now this is a very difficult case to analyze, But in this difficult case to analyze, there is a special case where velocity v, electric field E, and magnetic field B are such that the electrostatic field or the electrostatic force, which in this case is upwards, is cancelling out the magnetic force on the particle which is downward. So this is a very special case. This is a very special case, and most of the question that you are going to get in this particular case would be the situation where the electric and magnetic force are cancelling each other out. That means the acceleration of the block is zero. That means the electric force, which is in this case is upward, is cancelling out the magnetic force which is downward. So you get this scenario: Q into E is equal to Q into V into B into sine of 90, or you get the velocity of the particle equal to E by B. And this is a very peculiar case. So we are not solving the entire thing. We are not solving how the different cases here. We are only seeing one particular case, and in that one particular case, the net force is zero. The electrostatic force is cancelling out the magnetic force, and that is the only case that is going to come for you. So please note it down. Then this is a question: a particle of some charge moving with some velocity, so negative charge, along x-axis enters a region where there is a magnetic field along y-axis and an electric field along negative z-axis. If the charged particle continues moving along the x-axis, what is the value of the magnetic field? So as you can see, in this case, all the three things are parallel and the particle is still moving in a straight line. That means the electrostatic force Q into E is definitely cancelling out the magnetic force. So E becomes V into B, or your V becomes E by B. V is known, E is known. You can calculate the value of B, and I think it is coming as 10 raised to the power 3 Weber per meter square. So that is the answer. Any question that comes where you have electrostatic and magnetic field and the particle is moving in a straight line, it has to be a question of this nature. So please be careful and remember this. This is again a question. An electron moves inside a charged parallel plate capacitor. So this is a parallel plate capacitor. As you can see, charge density is sigma, which is the positive plate, which is the negative plate. It is not shown anyways. The space between the capacitor is filled with a constant magnetic field of induction B. Time of straight line motion. How much time it will take to cross the plates, basically they are asking. And it is moving in a straight line. I will give you 2 minutes to get me the answer. Option B, I think, is the correct one. In fact, even if you don't know anything about this question, you can still solve it. Looking at the options, all the options are dimensionally different. All the options, if you look at it, are dimensionally different. Only one option will have correct dimension, and that option has to be the correct one. Anyways, it is moving in a straight line, so the velocity with which it moves will be equal to E by B. Yes or no?
Yes.
Remember, E by B will always give you the dimension of velocity. So the velocity it will be moving will be equal to E by B. Electric field between the capacitor plates is given by sigma by epsilon naught. Yes or no?
Yes.
So that is the velocity. How much time it will take? It is moving with a constant velocity and it has to move a distance of L. So the time taken will be equal to L by V. As soon as you write this, your answer becomes absolutely simple. Epsilon naught LB by sigma. The only option that matches this, you could have found out it using dimensional analysis. Remember these small things. E by B is always equal to the dimension of velocity. So remember these small things. If you remember these small things, you will do a lot better in your exam. So that finishes our discussion of magnetic force on a charged particle. Now I'll give you 2-3 minutes. Go back. See if there is anything, any question, any particular topic up till now in magnetic force that you have not understood. Any question? I'll give you 5 minutes. Why I'm giving you this time? Because we are not going to get any time to revise it. Giving you 5 minutes. Go through this. If there's anything, let me know. Else we will start with the next one. Then you move on to the next heading, and this is force on a current carrying wire. Force on a current carrying wire. Now, what do you mean by force on a current carrying wire? Suppose we have a wire of random shape and we have this small segment of the wire of length dl. This wire carries a current and this wire is placed in a magnetic field. The magnetic field at this point is B. Now it has been found out that this wire, the small segment of the wire, this current carrying element, will experience a force. If I say that the df, small force df that this experience, on what all factors does this small force dl depend on? Df depend on, yes. On what all factors which the small force df depend on? It will depend on the current in the wire. It will depend on the length of the current carrying element. It will depend on the value of the magnetic field. Apart from this, it also depends on one more thing. What is that thing? It depends on the angle between the current carrying element dl and the magnetic field. If I put all these things together, the force acting on this small segment of the wire becomes I dlb sine theta, and that is the next heading, force on a current carrying wire. In this case, this is the force on a current carrying segment of the wire or current carrying element. Force is a vector quantity. What is this equation going to give me? Will it give me the magnitude? Will it give me the direction? Or will it give me both magnitude and direction of force?
Only magnitude.
Only magnitude, and therefore I will call it the scalar equation of force because it only gives me the magnitude. If there is a scalar equation of force, then there must be a vector equation. How does the vector equation of this force look like? df becomes df vector and this becomes I into dl cross b. This now becomes the vector formula of force, which will give me what? If I put everything in vector form, I put the value of the current carrying element in vector form, magnetic field in the vector form, I will get the force in the vector form, that means I will get magnitude as well as the direction. But I'm not going to use this, I'm going to use the upper one. If I am going to use the upper one, I have to find out some way of getting the direction of the magnetic force. And what is that way to find out the direction of magnetic force? To find out the direction of magnetic force, I am going to do the cross product of dl with b, the cross product of dl with v will give me the direction, and I can find this direction using the right hand thumb or the right hand palm rule. Your thumb will go in the direction of current carrying element. Right now this current carrying element is up. Your palm will go in the direction of magnetic field. The direction of magnetic field is like this. Then your fingers will give you the direction of force. Then the direction of your fingers will give you the direction of force. If I use that, dl is like this, magnetic field is like this. The direction of force on this gentleman would be inside. Do we understand this, or this has gone above our head saying bye bye? Bye bye. Bye bye. Bye bye. I'm going bye bye. Bye bye.
We got it.
Give you 1 minute to note this down. Then you can see this force is the cross product of dl and magnetic field, and therefore it will be perpendicular. This f vector or df vector will be perpendicular to both dl vector and b vector. Do we understand this? And it is shown in this way. It's given by the right hand thumb rule. The first vector, which is the dl vector, thumb should point in the direction of dl. The direction of dl is same as the direction of current. So thumb will go in the direction of current. Your palm will go in the direction of magnetic field, and the direction in which your finger curls will give you the direction of force. Current, field, force. I, B, F. I, B, F. I, B, F. Do we understand this? So this has gone above our head saying bye bye.
We understood.
Bye bye, sir. Bye bye, sir. Bye bye, sir. I'm going. Now you can do a special case. A special case. If magnetic field is uniform and the wire is straight, if magnetic field is uniform and the wire is straight, then what will happen? You have a straight wire like this, carrying current I, and let us say the magnetic field is inside, uniform and straight, uniform. Then the force will become how much? Let me not make the magnetic field like this. Let me make the magnetic field at an angle so that that angle comes. And the magnetic field is like this. Wire is straight and the magnetic field is like this. Then your force vector will become integral of I dl cross b, yes or no? Force, the total force will be the integral, yes or no? If I find out the integral, everything will come out. The integral of dl will become L. So in that case, the formula will become, vector formula of force will become I L cross B. Do we understand this?
Yes, sir.
Yes or no? No, yes.
Yes, sir.
This will be the vector formula that will give you both the magnitude and the direction of force. If you want to write the scalar formula will become, instead of dF, total force F will be equal to I L B sine theta. Where what is theta?
Angle between I and B.
Angle between the current carrying element or current and B. If theta is 0 or 180 degrees, this force will be 0. If theta is 90 degrees, this force will be maximum, and the maximum force will be ILB. I'll give you 2 minutes to note this down. Now let us see if you can solve this question. We have a rectangular loop of wire A, B, C, D. This wire carries a current I. It is placed in a magnetic field which is going inside. The length of this wire is L. The breadth of this wire is B. You have to find out the forces on magnitude and direction on all the four different segments and the force on the entire loop. I'll give you 2 minutes to give me the answer for this one. Before solving this question, what you can do is you can write a simple point that if the wire is straight and the magnetic field is uniform, where you can assume that the force is acting. If the wire is straight and the magnetic field is uniform, you can assume that the force acting on the wire is acting at the midpoint of the wire. So you may just assume it. The force on the wire for a straight wire placed in a uniform field, my dear friends, would be acting at its center or the midpoint. Once you have done that, then you can go ahead and solve the question. I'll give you 2 minutes to do it. You have noted down the question, yes or no?
Yes, sir.
I'll give you 2 minutes to solve it and give me the answer. What is the magnetic force? Now, if I talk about the forces on individual wires, if I call the force on this wire, what will be the force? What will be the force on this wire? Force on the wire AB.
IAB, sir.
So, the force on the wire AB will be I into L into B. What would be the direction of this force? When
Upward,
it
sir.
is like this, magnetic field is here, the force would be going in the upward direction at the center. Yes or no?
Yes.
The direction of this force would be upwards. If I find out the magnitude of force on the wire BC, what will be the force on the wire BC?
I small b capital B.
I into B into capital B, angle is 90. What will be the direction of force? Current is here, magnetic field is inside. What will be the direction of force?
Towards left, sir.
It would be like this. Are we able to understand this, or this is going above our head saying bye bye?
We understood.
Force on the wire CD will be how much?
ILB, sir. Towards downward.
ILB. And you can see the direction will be coming downwards. Force on the wire DA will be how much? I into B, and you can see that the direction will be like this. If I find out the force, the net force on the net force on the loop is 0. Now this is a very important concept that we have understood, that the force on a closed loop of wire which is placed in a uniform magnetic field, force on a closed loop of wire which is placed in a uniform magnetic field is going to be 0. Do we understand this?
Yes.
An important point, since we have done it for a very simple case, but even if we do it for a complicated case, any loop, you will get the same answer. Force on a closed loop placed in a uniform magnetic field is 0. Remember, it does not depend on size or shape. It also does not depend on direction. It only depends on two things. The first thing is that the loop should be closed. The second thing is the magnetic field has to be.
Uniform.
If you have a closed loop placed in a uniform magnetic field, the force acting on the loop, the net force acting on the loop is always going to be 0. It does not depend on the size or the shape or the orientation or the direction in which that loop is kept. I'll give you 2 minutes to note this down. So this is again a confirmation of the same fact. If you have a closed loop, coil, current carrying closed loop or coil of any size, any shape, placed in a uniform magnetic field, the net force acting on the loop has to be 0. The torque may or may not be 0. We'll come to this torque, don't worry. But if it is a closed loop placed in a uniform magnetic field, net force is 0. But if it is placed in a non-uniform field, well, then the magnetic force is not going to be 0. Do we understand this? When I say uniform magnetic field, the magnetic field must be constant in magnitude and constant in direction. Do we understand this? Yes
Yes.
or no? You have 2 minutes to note down. Now we have seen that the net force acting on the loop or a closed loop is 0. Now this concept can be used to find out the force on any arbitrary shape current carrying conductor. Suppose you have an arbitrary shape current carrying conductor like this, the pink one, and you are supposed to find out what is the force acting on this arbitrary shape loop. Remember, this arbitrary shaped loop is placed in a uniform magnetic field. We are only dealing with the cases where the magnetic field is uniform. Do we understand this?
Yes.
So if this arbitrary shaped loop is placed in a uniform magnetic field and it carries current in the pink direction, What you can do is you can close this loop by drawing a green line. Do we understand this? You
Yes.
can close this loop you can close this loop by drawing this green line. Whatever force is acting on the pink line, if you close that loop, the net force acting on the loop will become zero. Yes or no?
Yes, sir.
That means whatever force is acting on that pink line, the same force will be acting on the green line going from B to A. Or if I draw this green line from A to B, whatever force is acting on that pink line, the same force will be acting on this green line. Yes or no?
Yes,
The
sir.
direction is also same. Do we understand this?
Yes.
Using this concept, you can find out the magnetic force acting on any shape wire which is placed in a uniform magnetic field. You just have to join the two ends of the wire with a straight line. Whatever force is acting on the curved part, the same force would be acting on the straight path in the same direction. Do we understand this?
Yes.
I'll give you 2 minutes to note this down. Then you can use this concept and you can find out the force. Let us say if I have an arbitrary shaped wire like this placed in a uniform magnetic field, what will be the force acting on this wire? You just have to join it by a straight line. This is the straight line which I have joined this. So the force acting on this pink wire will be same as ILB. Do we understand this?
Yes, sir.
What will be the force? These are three questions that I have made for you. What will be the force acting on this wire in first case? All the wires are semicircular. This is case number A, this is case number B, this is case number C. Yes. I'll give you 2 minutes to note, get me the answers.
B2R.
In first case it is
IB2R. And it is outside.
I into B into 2R and the direction is
Outside, sir.
outside. Second case,
0, sir.
third case,
It is IB2R and it is upward, sir.
do we understand this? Yes or no?
Yes.
Then this is the next question. Two long wires carrying current I1 and I2 are placed perpendicular to each other in such a way that they avoid a contact. Find the magnetic force on a small element dl of the second wire situated at a distance of L from the first wire.
ID
Yes,
magnetic force is IDL mu naught by 2 pi L, sir. Sorry, mu naught I1 by 2 pi L and it is upward, sir.
mu naught
I1 2 pi L.
mu naught I1 2 pi L.
Yes, sir.
You have to find out the magnetic force on this wire of length dl carrying a current I2. What is the answer?
IDL mu naught I1 by 2 pi L, sir.
So first of all, you have to find out the magnetic field. The magnetic field is mu naught I1 by 2 pi L. I1, we have to multiply it by I2 into dl. That will be the magnetic force, and the direction, the magnetic field is inside, yes or no? So
Yes, sir.
dl cross b, the force will be in the upward direction. So that is the answer. The force is in the upward direction, and the value is mu naught I1 I2 dl by 2 pi l. Do we understand this?
Yes, sir.
Everyone understands this?
Yes, sir.
The next heading that we are going to write is force between two parallel wires. If I have two very long parallel wires carrying current I1 and I2 separated by a distance A, then with what force these two wires are going to attract each other? If I consider a length L of the other wire, the force would be equal to mu naught by 2 pi into I1 I2 by A into L. Yes or no? Yes or no?
Yes, sir.
Do we understand this? That the force will be equal to this value. We will find out the magnetic field due to the first wire, and we multiply it by the current and the length of the second wire. Yes or no?
Yes, sir.
That means if I calculate the force per unit length, the force per unit length will be given by mu naught by 2 pi into I1 I2 by A. Yes or no? Newton per meter.
Yes, sir.
Do we understand this? Yes or no?
Yes, sir.
Now if I replace, now if I put the value of I1 and I2 as 1 ampere and the distance as 1 meter, how much will the force become? If I1 and I2 are replaced by 1 ampere and the distance is made 1 meter, the force will become 2 into 10 raised to the power minus 7 Newton. Yes or no?
Yes, sir.
That gives us the definition of 1 ampere. How much is 1 ampere? Please listen to me, then I'll give you the time to write. When too long, not large, current carrying wire carries equal current and are they separated by distance of 1 meter, and they exert a force on each other which is 2 into 10 raised to the power minus 7 Newton per meter, then the current flowing in each of the wire will be taken as 1 ampere. This is the definition of 1 ampere. Do we understand this?
Yes, sir.
1 ampere is that current which, when flowing in two infinite parallel wires placed in vacuum at a distance of 1 meter, experience a force of 2 into 10 raised to the power minus 7 Newton per meter on each other. Do we understand this?
Yes.
Do we understand this? Do we understand this?
Yes, sir.
What is the direction of this force? And remember, it's a very important concept. If the wires are carrying current in the same direction, you can find out that the force is going to be attractive. So remember this, in the same direction when they carry current, the force is going to be attractive. If they carry current in the opposite direction, the force is going to be repulsive. You can easily find it out. I will leave that task to you. So this is the force between two parallel wires. Per unit length, the force is mu naught by 2 pi I1 I2 by A. That also gives us the definition of 1 ampere. If the wire carry current in the same direction, it is attractive E. If it carry current in the opposite direction, it is repulsive. Do we understand this?
Yes.
I'll give you 2 minutes to note this down. Then we can just see this force between charges. That is how we started. Two charges Q1, Q2 separated by a distance of r. The electrostatic force between these two charges will be 1 by 4 pi epsilon naught Q1, Q2 by r square. Do we remember this?
Yes, sir.
Yes or no?
Yes, sir.
Now remember, if these two charges are same, like charges, and they are moving in the same direction, with the same, they are moving in the same direction, they will again be attracting each other. We can easily understand this. Now, this magnetic force will be attractive. Can anyone tell me what is the form? What would be the formula of this magnetic force between the two particles? Having charge q1, q2, moving at velocity v1 and v2. What will be the magnetic force between these two particles? The magnetic force between these two particles will be mu naught by 4 pi q1 q2 v1 v2 divided by r square. Now, if I find the ratio of magnetic force by the electric force, you will see that that ratio will be equal to this one, and you must know that mu naught into epsilon naught is 1 by c square. So the ratio of magnetic force to the electrostatic force would be v by c whole square, and you know that v is going to be very less, and therefore your magnetic force is going to be very less compared to the electrostatic force between the two charges. I hope you have understood this. Yes or no?
Yes, sir.
I'll give you 2 minutes to note this down. Then you can solve this question. You have to find out the force on the loop. The name of the loop is PQRS. To find out the force on this loop. This is an infinite current carrying wire. So, how are we supposed to do this? Now, if I look at this wire and if I look at this wire, now both this pink wire and the green wire, the magnetic field is it constant or is it varying?
Varying, sir.
So, in order to find out the force on these two wires, you will have to integrate it. But here the question is not to find out the force on the wire, the question is to find out the force on the loop. If you look at the pink wire and you look at the green wire, they are placed in variable field. But is the force acting on both the wires same in magnitude or not?
Yes, sir.
Will it be same in direction?
Opposite in directions.
Therefore, both the forces will do what?
Cancels.
Both the forces will cancel out each other, so you don't have to calculate these two forces. Now, talking about the force on this wire, whether this wire would be attracted or will it be repelled?
Repelled, sir.
To take deep breaths, deep breaths. Calm yourself down. Close your eyes. Open them slowly.
Sir, you are asking PQ, RS, or long current carrying wire or PQ?
Look at the question. Understand the question. I'm asking the force on the blue wire. Will it be attractive or will it be repulsive?
Due to which one, sir? Due to RS or due to I?
What are you finding here? What is the question? Did you understand the question, beta?
Yes, sir.
What was the question?
Find the force on the loop due to current carrying conductor. Sir, current carrying wire.
Now I ask the question again. What is the force on the blue wire? Which force I would be asking?
Force due to I
What is the answer?
is mu naught by 2 pi into I1 I2.
Attractive or repulsive?
Attractive, sir.
Thank God. Attractive the force is. What is the value of this force?
I2 mu
Mu
naught
naught I by 2
I2.
pi A into I2 into A. Yes or no?
Yes, sir.
Chalo. What about the force on this wire? Attractive or repulsive?
Repulsive, sir.
How much?
Mu naught by 4 pi.
Mu naught I by 2 pi, not 4 pi,
Sir, after into 2A.
into 2A multiplied by I2 into A. And it will be repulsive. Which force is going to win? The attractive one or the repulsive one?
Attractive one.
So what is the net force on this loop? The net force on this loop would be attractive. And what is the value of the net force?
Mu naught I2 by 4 pi, sir.
Mu naught I2 by 4 pi. Do we understand this or this has gone above our heads saying bye-bye?
Understood, sir.
Okay, that takes us to the next, and instead of solving these 7 or 8 questions, what I am going to do is giving you all those questions as points. So you will take them as points and you will remember them. Do we understand this?
Yes, sir.
So some cases of questions that can come. The first variety of questions that can come, again these are questions and you just have to remember them as points. Is no point of understanding how it is done. You don't have that much of time. Now if you have any arbitrary shape current carrying loop in a uniform magnetic field which is perpendicular to the loop, remember, perpendicular to the loop. Now, because of the force acting on the loop, it's an arbitrary shaped loop. Because of the force acting on the loop, this loop is going to stretch out and convert itself into a circular loop. Do we understand this?
Yes, sir.
Remember this. And the tension in the loop, they are going to ask you what is the tension in the loop. The formula for tension in the loop will be BIL by 2 pi. What is B? What is I? What is L? What is 2 pi?
Sir, B is magnetic field, I is current in the loop, L is
Length of the loop, and 2 pi is 2 pi. Do we understand this? Now
yes,
this has gone above our heads. saying bye bye.
Understood, sir.
Bye bye. I'll give you 2 minutes to note this down. Okay, then you can see this case, which is the case of equilibrium of free wire. Here, what we have done is we have a fixed wire and we have a wire which is free. A wire which is free. Now, because of the this wire is free, so you have this gravitational force which is trying to pull the wire down. Yes or no?
Yes, sir.
Now, if you can have current in the opposite direction in the two wires, what will happen is because of this current in opposite direction, the wire will repel each other, and there could be a case where the wire is in equilibrium. Yes or no?
Yes, sir.
If the wire is in equilibrium, then this condition would be met. The force per unit length of the wire will be equal to the mass per unit length multiplied by G. Yes or no? The upper wire can remain in equilibrium if it is disturbed from this position. It is going to perform SHM, and the time period of SHM would be given by this. Remember, this type of equilibrium condition when the upper wire is free and the lower wire is fixed is stable equilibrium. Do we understand this?
Yes, sir.
Because if you move it downwards, the force will increase and it will try to push it upwards. Therefore, it is in stable equilibrium. We understand this, or this has gone above our head. Saying bye bye.
Understood, sir.
Okay. Then there is this opposite case where the lower wire is free and the upper wire is fixed. Now, for this wire to stay in equilibrium, the two wires must attract each other. The direction of current is given reverse. So just correct it. Both the wires should carry current in the same direction. Do we understand this?
Yes, sir.
The wire can remain in equilibrium. For equilibrium, this condition must be met. The force per unit length must be equal to the mass per unit length multiplied by G. Do we understand this? But this type of equilibrium, my dear friends, is going to be unstable. Why it is going to be unstable? If I move it downward slightly, the attractive force will decrease and it will never be able to come back. If I move it upward slightly, the attractive force will increase and it will be moving back to a, and it will be moving up and it will be going on the other side to the stable equilibrium. Do we understand this? So this is the condition of stable equilibrium. This is the condition of unstable equilibrium. Do we get this?
Yes, sir.
I'll give you 2 minutes to give me 2 minutes to note this down. Then this is the next case. You have a current carrying loop and current carrying wire. You have to find out the force on each other. Remember the force, whether you find out the force on one, whether you find out the force on the current carrying loop because of the wire, or you find out the force on the current carrying wire because of the loop, both the answers are same. Do we understand this? Yes or no?
Yes, sir.
Now, if this current carrying wire is placed at the center in a direction which is perpendicular to the direction of magnetic field, then only it will experience force. If it is placed in the same direction along the axis, it will not experience any force. Do we understand this? Because magnetic field of this loop will be pointing in this direction. Do we understand this? Magnetic field is like this. So if I place the loop like this, if I place the wire like this, it will not be experiencing any force. But if I place it at the center in a direction which is perpendicular, the force would be given by this formula. Do we understand this?
Yes, sir.
All these are questions that I'm giving you as points. Give you 2 minutes to note this down. Then you can look at these two cases. Current carrying spring. There is a spring which is attached to a block, and if you pass the current through the block, if you pass the current through the spring, the current will be moving in the same direction through all the coils. So all the coils will be attracting each other, and therefore the spring will contract when current passes. Do we understand this?
Yes.
Yes or no?
Yes, sir.
Similarly, you have a current carrying wire of mass m hang like this. If you pass current through this, there can be a case where the force experienced by this wire can be equal to the gravitational force. In that case, the tension will become zero. For tension to become zero, the force of gravitation must be balanced by the magnetic force. ILB sine 90 will be equal to mg. From there, you can get the value of I, for which the tension in the string becomes zero. We get this, yes or no?
Yes, sir.
I'll give you 2 minutes to note this down. Then these two are the other two cases. In case number 6 is exactly almost similar to case number 5. Here the wire is suspended in anger. The angle between the current carrying element, the current carrying wire, and magnetic field is given as theta. This wire is suspended in air. The magnetic force must be equal to the weight. Do we understand this?
Yes, sir.
In the last case, this question actually came in one of the JEEs, IIT-JEE. The wire is moving with a constant velocity. When the wire is moving with a constant velocity, the gravitational force mg sine theta, which is trying to pull it down, must be equal to this f cos theta. From there, you get this relation of wire moving with a constant velocity. What should be the value of the magnetic field? Do we understand this?
Yes, sir.
2 minutes, you have to note it down. This is the first question. A vertical current carrying wire carry current in the upward direction, placed in a horizontal magnetic field towards north. What will be the direction of force? Yes. Give me the answer first. No answers?
West, sir.
And the answer is definitely west. This is north, south, east, west. Current is upwards. DL, B is here. So it has to be towards west, and that is the answer. Do we understand this? Yes or no?
Yes, sir.
This is the next question. This question primarily relies on your ability to calculate and whether you know the relation between Gauss and Tesla. I'll give you 1 minute to solve this. So the answer here is you have to find out the force on this wire ILB sine theta. The only thing you have to understand is all the answers are different in just terms of the power. So you basically have to convert Gauss into Tesla. 1 Gauss is 10 raised to the power minus 4 Tesla. If you put the values, you will get the answer as option C, and that is the answer for this question. Let's not waste any more time on this one, and let us move ahead. Have we understood what you have to do, what has to be done there?
Yes.
This is the next question. A conductor PQRSTU is placed like this. It is in 3 dimensions. It is placed in a uniform magnetic field directed parallel to positive y-axis. What is the force experienced by this wire and the direction? So how are we supposed to solve this? The force acting on this loop will be same as the force acting on this wire. Yes or no? So what is the force acting on this wire? I into L into B into sine of 90. Only option that matches with ILB is this one. So the correct answer is this. Current is here, magnetic field is here, force will be in the upward direction, and that is the answer for this one. Do you understand how this is done?
Yes, sir.
Then comes the next question. This one, a conductor in the form of a right angle triangle ABC, AB is 3, BC is 4, carries a current 10 ampere, AB and BC. There is a uniform magnetic field 5 Tesla perpendicular to the plane of the conductor. What is the force on the conductor? The conductor has two sides, AB and BC. It's in the form of a right angle triangle. Right angle, not triangle. The conductor is in the form of a right angle. Diagram is not given, and I don't have time for you to waste, so I'll show you the diagram. Diagram looks like this. One side is 3 centimeter, the other side is 4 centimeter. You have to find out the force on the wire, and the answer is what is the answer?
2.5 Newton.
2.5 Newton. That is correct. You just have to join the two ends of the wire and you end up with your answer. I hope we have understood this. Yes or no? No or yes?
Yes, sir.
This is the next question. This question has been taken from previous year IITs. A current carrying loop, a conducting loop carrying a current is placed in a uniform magnetic field pointing into the plane of the paper as shown. So the diagram is there. So I'll have to show you the diagram. That diagram is not there. So this is a current carrying loop. I have drawn it like this. This is a current carrying loop. It is placed in a magnetic field which is coming out. What will happen to the loop?
Sir, diagram is not visible.
What is the answer for this one? So the answer is, I've already given you, this is case number 1. The loop will expand and become a circle. We know this?
Yes, sir.
This is the next question that comes into the picture right now. A circular loop of current carrying current I. A circular loop of radius A carrying current I is placed in a two-dimensional magnetic field. The center of the loop coincides with the center of the field. If you can see, the field is going radially outward. I hope you can understand. At this point it is here, at this point it is here, at this point it is here. I hope you understand what type of magnetic field this is. Do we understand this?
Yes, sir.
You have to find out the force on this wire. I'll give you 2 minutes to give me the answer. Option D is the correct option. At all the points, the angle between the magnetic field and the current carrying element is 90 degrees. At all the points, the magnetic force will be going in the same direction. So you have to add up all these forces. To add up all these forces, you have to integrate dl. If you integrate dl, you will get 2 pi r. So 2 pi r into I into B. Do we understand this? Yes or no?
Yes, sir.
This is the question. Next one. It came in one of the IITs. A current carrying wire is kept in the xy plane is in the form of a sine wave. The diagram is not a part of the question, but I will show you the diagram so that you can do it quickly. Time is not on our side. So the diagram is like this. You have to find out the force on this wire. I'll give you a minute to do this. Option A is the correct answer. What you got to do is do nothing but join it like this. Yes or no?
Yes, sir.
Whatever is the force on this straight wire, which has got a length of lambda, that is the force on that curved wire. I lambda into B is the answer. Everyone understands this? Yes or no?
Yes, sir.
Then you move on to the next topic, which we have already covered. Current carrying loop as a magnetic dipole. Do we remember this? Yes or no?
Yes, sir.
A current carrying wire or current carrying loop produces a magnetic field, so it can behave same as a dipole. How do you find out the dipole moment? NIA. Do we remember this? Yes or no?
Yes, sir.
If it is a straight wire, the magnetic dipole moment is taken as 0. Straight wire does not have a dipole moment. The dipole moment is only characterized with a closed loop of wire. If it is a square of length A, the total length is L. Side length will become A. The magnetic dipole moment will become like this if it becomes a same length. If it becomes equilateral triangle, the dipole moment will become like this. If it becomes circle, remember the area of a circle for a given length is maximum. Do you know this? For a given length, for a given perimeter, the area of a circle is the maximum. Do we know this?
Yes, sir.
Therefore, the magnetic moment of a circle will be maximum. You can note this down as a point. Do we understand what I have said here?
Yes.
2 minutes you have to note it. Then we move to the last topic of this chapter, which is magnetic dipole in a magnetic field. We have seen that if you have a dipole which is placed in a uniform magnetic field, the net force acting on the dipole is 0. Yes or no?
Yes, sir.
But the net torque may not be 0. Now this dipole may be a magnet, or this dipole may be a current carrying loop. Do we understand this?
Yes, sir.
It will experience a torque, and the torque is given by mb sine theta, where m is the magnetic dipole moment, b is the magnetic field, and sine theta. Theta is the angle between dipole moment and the magnetic field. Do we understand this?
Yes, sir.
This torque will be 0 if the angle is 0 or 180 degrees. This torque will be maximum when the angle is 90 degrees. Do we understand this?
Yes, sir.
When the angle is 0, when the angle theta is 0, that is the condition of stable equilibrium. Do we understand this?
Yes, sir.
When the value of theta is 180 degrees, that is the condition of unstable equilibrium. Do we understand this?
Yes, sir.
Okay. Now, if you replace the magnet by a magnetic dipole, everything remains same because a current carrying coil behaves like a dipole. Everything remains same. Do we understand this? So whatever we are going to do for magnet, the same thing is valid for magnetic dipole. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Well, then these are the points that you already know. Just to note them down. Torque is an axial vector. I told you that, yes or no?
Yes, sir.
Now, this torque, what is it is trying to do? It is always trying to bring the loop back to its stable equilibrium. And the stable equilibrium is the equilibrium where M and B are in the same direction. So it will always try to rotate the loop such that the magnetic moment M comes in the same direction as B. Do we understand this?
Yes, sir.
In a uniform magnetic field, net force is 0, torque may or may not be 0. In a non-uniform field, force is not 0, torque may or may not be 0. If the angle is 90, torque is maximum. If the angle is 0 or 180, the torque is 0. Do we understand this?
Yes, sir.
2 minutes you have to note it down. Then let's move on to the next heading, that is the potential energy of a dipole in a magnetic field. And the only formula that you have to remember about potential energy is minus mb cos theta, or in vector form it is minus m dot b. This is the potential energy of a magnetic dipole in a magnetic field. If m and b are parallel, the potential energy is minimum, and that is the condition of stable equilibrium. If M and B are anti-parallel, the potential energy is maximum, and that is the condition of unstable equilibrium. If they are at 90 degrees, the energy is 0 and there is no equilibrium. Do you understand this? Yes or no?
Yes, sir.
I'll give you 2 minutes. Do it fast. The last thing in this particular topic is work done in rotating a dipole. We have done this thing right from the chapter on gravitation. Work done by electrostatic or magnetic force is energy in the first position minus energy in the second position. If the work is done by the external force, it is energy in the second position minus energy in the first position. If the change in kinetic energy is 0. Do we remember this?
Yes, sir.
Yes or no? Now remember, whatever we have done for magnetic dipole or a current carrying loop, the same thing is valid for an electric dipole. Electric dipole or a magnetic dipole. Do we understand this? I'll just show you this. The only difference is wherever we have M, In an electric dipole, that M will be replaced by P, where P is the electric dipole moment. Do we understand this?
Yes, sir.
Wherever there is B, magnetic field, it will be replaced by E, electric field. Do we understand this?
Yes, sir.
So this is just a comparison of electric dipole plays in an electric field and magnetic dipole plays in a magnetic field. Both the concepts are similar. Instead of M, we have P. Instead of B, we have E. Do we understand this?
Yes, sir.
Same for all the formulae. In the previous case, the torque on an electric dipole will be P cross E. Do we understand this?
Yes, sir.
The potential energy of an electric dipole will be minus P dot E. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note them down quickly. Okay, then great. There is one more table. I mean, everything that we have done is in this table. You can note this table down. You don't have to note this table down. You already know this table. So everything that we have discussed is there in this one table. You can see if the electric field and the dipole moment are in the same direction, it is the stable equilibrium. If they are in the opposite direction, it is unstable equilibrium. At 90 degrees, the torque is maximum. Do we understand this?
Yes, sir.
The potential energy is minimum in case of stable equilibrium. The potential energy is maximum in case of unstable equilibrium. The same thing has been given for a magnetic dipole. It is not said whether it's a current carrying loop or it's a magnet. Whether it's a current carrying loop or it's a magnet does not make any difference. The formula remains same. Do we understand this?
Yes, sir.
And sometimes they also ask you the time period. If it is uh, if it is performing SHM, what is the time period? Oops, what has happened here? If if it is performing SHM, what is the time period? So remember the time period for SHM for an electric dipole or time period of SHM for a magnetic dipole is given by this formula: 2 pi root over I by P, 2 pi root over I by MB, where what is I? I is the moment of inertia of the dipole. Do we understand this?
Yes, sir.
Well, that takes us to the end of this particular topic, this particular chapter. We are done with magnetic field. We are done with magnetic force. Everything that was possible for me to cover that can come, that is a part of your curriculum. I have done everything and some extra things as well. I have not left anything on purpose. Anything that could have come, anything that was a part of your course has been covered. I hope you understand this. In the next class, we will start with EMI, electromagnetic induction, and we'll try to wrap it up and take maybe 3 or 4 classes to wrap it up. Then what is left is AC, and then what is left is EM wave. So I will try to wrap it up in the next week by all probability. I hope you have understood what we have done in today's class. Yes or no?
Yes, sir.
You have understood the concept of dipole and that formulas and all that?
Yes.
Okay, then I'll see you tomorrow. Take care and God bless you all. Bye bye.